The engineer paused, her hands hovering over the device. This was the culmination of decades of work. Work that had been hidden from the public. Work that might change our understanding of physics forever. She glanced at her colleagues, a silent acknowledgement passing between them. They all knew what was at stake. With a steady hand, she made the final adjustment and activated the system. For a moment, nothing happened. Then, a shimmer in the air, a distortion in space itself. And suddenly, they were looking at something that, according to conventional understanding of physics, shouldn't exist. They had done it. The impossible was now possible. And all of this happened behind the secure perimeter of the most secretive military installation on Earth, deep within the Nevada desert, at a facility the public knows as Area 51. For decades, Area 51 has captured the imagination of the public. Conspiracy theories abound, from crashed alien spacecraft to secret meetings with extraterrestrial beings. But the truth, as is often the case, is simultaneously more mundane and more extraordinary than the fantasies. Area 51, officially named Homey Airport or Groom Lake, has long served as a testing ground for the most advanced aircraft and surveillance systems on the planet. But what many don't realize is that beyond the runways and hangars lies something even more secretive. A division dedicated to pushing the boundaries of space technology, developing systems that seem to defy our current understanding of physics. A place where the line between science fiction and science fact blurs into something unrecognizable. But how did we get here? How did a remote location in the Nevada desert become the epicenter of humanity's most advanced technological research? And what's really happening inside those walls today? The answers to these questions are complex and layered, requiring us to peer into both the depths of history and the frontiers of human knowledge. And so our journey begins not in the desert sands of Nevada, but in the urgency and paranoia of the Cold War, when the very survival of nations depended on technological superiority. In the aftermath of World War II, tensions between the United States and Soviet Union escalated rapidly. Both superpowers recognized that dominance in the skies would be critical in any future conflict. The need for advanced reconnaissance aircraft became paramount, vehicles that could fly higher and faster than anything previously conceived, capable of penetrating enemy airspace undetected. In 1955, Lockheed's Kelly Johnson proposed the IDE U-2 spy plane, an aircraft designed to fly at altitudes of 70,000 feet, well beyond the reach of Soviet interceptors and anti-aircraft systems of the time. The U.S. government needed a remote, secure location to test this revolutionary aircraft. Far from prying eyes and Soviet spies, they found their answer in a dried-up lakebed in Nevada, a location so remote that even most government officials were unaware of its existence. And thus, Area 51 was born. The site was chosen specifically for its isolation. Surrounded by mountains and already within a government testing range, it provided the perfect cover for highly classified projects. The U-2 program was just the beginning. As the facility proved its worth, it became the natural home for increasingly advanced aerospace projects, including the legendary SR-71 Blackbird, which to this day remains the fastest air-breathing manned aircraft ever created. But even as Area 51 focused on the development of advanced aircraft, something else was happening in parallel. Something that would eventually eclipse even these remarkable achievements. A small group of scientists and engineers, drawn from the most brilliant minds in the country, began exploring concepts that pushed beyond atmospheric flight and into the realm of space. This group would eventually become what insiders refer to as the Space Technology Division, though officially, no such division exists in any public record. Indeed, the very existence of this division remained a closely guarded secret for decades, with information compartmentalized to such an extent that even many who worked at Area 51 were unaware of its activities. The division operated under multiple layers of security and secrecy, with projects given cryptic code names and research distributed across different teams, each unaware of the full scope of what they were creating. But why such extraordinary measures? What technologies could possibly warrant this level of secrecy? The answer lies in the nature of the division's work. From its earliest days, the Space Technology Division focused on concepts that were considered either impossible or decades ahead of their time. Propulsion systems that didn't rely on conventional rocket fuel, materials that could withstand the extreme conditions of space, communication systems capable of transmitting data across vast cosmic distances, and perhaps most tantalizing of all, the exploration of physics beyond the standard model, venturing into realms where our current understanding breaks down. Let's start with propulsion, perhaps the most fundamental challenge in space exploration. Conventional rocket technology, while proven and reliable, is inherently limiting. The tyranny of the rocket equation dictates that to achieve significant velocity, a rocket must carry enormous amounts of fuel, which itself adds mass, requiring even more fuel in a diminishing returns scenario. This fundamental limitation has constrained our ventures into space, making ambitious missions to the outer solar system and beyond extraordinarily difficult and time-consuming. From the 1960s onwards, the Space Technology Division began exploring alternatives. Early work focused on nuclear propulsion, building on projects like NERVA, nuclear engine for rocket vehicle application, which demonstrated that nuclear thermal rockets could achieve twice the efficiency of chemical rockets. But while nuclear thermal propulsion was promising, the division's scientists were already looking beyond it, towards concepts that might truly revolutionize space travel. One such concept was the electromagnetic drive, or M-drive, which first appeared in classified documents in the late 1980s, decades before it would become publicly known through independent researchers. The M-drive represented something extraordinary, a propulsion system that appeared to generate thrust without expelling any propellant, seemingly violating Newton's third law of motion. Essentially, a conical RF resonant cavity, the M-drive, converts electrical energy into thrust through mechanisms that remain controversial and poorly understood even today. The public versions of the M-drive, developed by researchers like Roger Scheuer and later tested by NASA's EagleWorks laboratory, have produced tiny amounts of thrust, so small that many scientists attribute the results to measurement error or unaccounted-for external influences. But documents that have emerged through declassification suggest that the Space Technology Division achieved significantly better results through refinements in the cavity design and the application of exotic materials that aren't available to the public sector. Another area of focus has been field propulsion, the concept of generating thrust by interacting directly with quantum fields, or even with the fabric of space-time itself. While public research in this area remains largely theoretical, there are indications that the division has made significant practical progress. In 2004, a patent application filed by the U.S. Navy for a high-frequency gravitational wave generator briefly appeared before being classified. The device described bore striking similarities to concepts developed decades earlier within the Space Technology Division, suggesting a possible transfer of technology from the classified to the semi-public domain. But perhaps the most fascinating propulsion concept explored by the division is the manipulation of space-time itself. In 1994, Mexican physicist Miguel Alcubierre published a paper describing how a specific configuration of energy could potentially contract space in front of a vessel and expand it behind, effectively moving a region of space-time and anything within it at speeds that could exceed the speed of light without actually breaking the cosmic speed limit within the local frame of reference. The so-called Alcubierre drive was considered purely theoretical, requiring negative energy densities that appeared impossible to achieve. However, internal documents suggest that the Space Technology Division had been exploring similar concepts. Since the 1970s, inspired partly by earlier theoretical work by physicist Robert Forward. While the public scientific community dismissed such ideas as impossible, the division approached the problem from multiple angles, looking for loopholes in the seemingly insurmountable energy requirements. And there are tantalizing hints that they may have found some. Reports of unusual gravitational anomalies detected by sensitive equipment near certain Area 51 facilities have occasionally surfaced, quickly dismissed as equipment malfunctions, but consistent with the effects one might expect from early experiments in space-time manipulation. Of course, propulsion represents just one facet of the division's work. Equally important has been the development of materials capable of withstanding the extreme conditions of space and exotic propulsion systems. Conventional materials simply aren't adequate for the stresses involved in advanced space travel, from high-energy radiation to extreme temperatures and pressures. The Space Technology Division pioneered work in what we now call metamaterials, engineered materials with properties not found in nature. Long before the term became common in scientific literature, the division was creating structures with precisely controlled electromagnetic properties. Some of these materials were designed to absorb radar, leading to stealth technology that would eventually be incorporated into aircraft like the F-117 Nighthawk. Others were developed specifically for space applications capable of shielding against radiation or dissipating the enormous heat generated by advanced propulsion systems. One particularly interesting area of research has been in materials that interact with gravity in unusual ways. Mainstream physics holds that gravity cannot be shielded against. Unlike electromagnetic forces, gravity simply passes through all known materials. However, theoretical work in quantum gravity suggests the possibility, however remote, that certain precisely engineered atomic structures might be able to attenuate gravitational waves or fields. The division reportedly made this a priority area of research, with some documents referring to a project codenamed Looking Glass that achieved promising initial results in gravity modification experiments during the mid-1990s. The development of these advanced materials wouldn't be possible without equally advanced manufacturing techniques. The division has long operated its own fabrication facilities, employing methods that have only recently become available to the broader scientific community. Advanced 3D printing of metal alloys, precision atomic deposition, and molecular self-assembly were all pioneered within the secure facilities of Area 51, often decades before similar techniques became known publicly. And what of energy sources to power these advanced technologies? Conventional power generation is woefully inadequate for the energy demands of cutting-edge space technology. While nuclear power offers significantly higher energy density, even this falls short for the most ambitious applications. Here, too, the Space Technology Division has pushed far beyond conventional boundaries. One approach has been to develop more efficient ways of harnessing nuclear energy. Beyond the nuclear thermal rockets mentioned earlier, the division explored compact fusion systems decades before similar projects appeared in the public sphere. While controlled fusion remains an elusive goal for public research, there are indications that the division achieved functional, if limited, fusion reactors as early as the 1990s, though the power output was likely modest by the standards of what would be needed for revolutionary space applications. Even more intriguing are references to research into zero-point energy. The notion that the quantum vacuum, far from being empty, contains enormous energy that might theoretically be tapped. While mainstream science has largely dismissed practical zero-point energy extraction as impossible, classified research has approached the problem from unique angles. Rather than attempting to extract macroscopic amounts of energy directly from the vacuum, which indeed may be impossible, the division reportedly developed systems that use small perturbations in zero-point energy to catalyze other, more conventional reactions, achieving efficiencies that would otherwise be unattainable. Communication represents another critical area of focus. Space exploration is fundamentally limited by our ability to communicate across vast distances. Radio waves, traveling at the speed of light, take minutes to reach Mars and hours to reach the outer planets. Any serious deep space exploration or potential colonization would require something better. The division's work in this area has largely focused on quantum entanglement, the phenomenon Einstein famously referred to as spooky action at a distance. When particles become entangled, the state of one particle instantaneously affects the state of the other, regardless of the distance separating them. In theory, this could allow for instantaneous communication across any distance, including interplanetary or even interstellar gaps. Public research in quantum communication has made significant strides, with China's MICUS satellite demonstrating quantum key distribution over thousands of kilometers. But the Space Technology Division's work reportedly goes much further. Documents suggest they achieved reliable quantum communication over much greater distances in the early 2000s, employing novel methods to maintain entanglement that haven't yet appeared in public scientific literature. There are even references to a system code named Quantum Bridge, described as capable of high bandwidth, secure communication, independent of light speed constraints. The implication is extraordinary. A functional communication system that operates outside the normal limitations of physics as we understand them. If such a system exists, it would revolutionize not just space exploration, but all of telecommunications. Behind all these technological marvels lies something even more fundamental, a different understanding of physics itself. The standard model of particle physics, combined with general relativity, has served science well, but we know it's incomplete. The two theories remain fundamentally incompatible, and phenomena like dark matter and dark energy stand as reminders of how much we still don't understand about the universe. The Space Technology Division has reportedly operated under different theoretical models, exploring the implications of alternative theories that might resolve these inconsistencies. Some of these approaches build on mainstream theories like string theory or loop quantum gravity. Others take more radical departures, exploring ideas that have been dismissed or overlooked by the broader scientific community. One particularly interesting thread involves the work of a physicist referred to in documents only as Dr. Wilson, who in the 1980s developed what was called a unified field approach that apparently resolved some of the contradictions between quantum mechanics and general relativity. The approach never appeared in public scientific literature, but subsequent technology developments within the division appear to have built upon this theoretical foundation. There are also indications that the division took very seriously the controversial work of Hungarian physicist Gabriel Krón, who in the mid-20th century developed mathematical models suggesting the possibility of extracting electrical energy from the geometry of space-time itself. While Krón's work was largely ignored or dismissed by his contemporaries, documents suggest the division found practical applications for his theories, particularly in the area of advanced power systems. This willingness to explore heterodox theories is reflected in the division's organizational structure and culture. Unlike conventional research institutions, which are often constrained by peer review and the consensus-driven nature of modern science, the Space Technology Division operated with a high degree of intellectual freedom. Ideas were evaluated not on their conformity to established theory, but on their practical results and internal consistency. This approach, protected from the ridicule or career penalties that often face scientists who venture too far from established paradigms, allowed for a unique kind of innovation. The division also appears to have taken a multidisciplinary approach that's rare in specialized scientific research. Teams combined experts from diverse fields, theoretical physics working alongside materials, science, engineering, and even biology. This cross-pollination of ideas created a fertile environment for breakthrough thinking, allowing connections that might never emerge in more siloed research environments. And what of the present and future? While much of our information about the Space Technology Division comes from historical documents and the occasional declassified report, there are strong indications that its work continues today, with even greater resources and more ambitious goals. The explosion of private space companies like SpaceX and Blue Origin has changed the landscape of space exploration, but these companies are still working largely with refinements of conventional rocket technology. Meanwhile, behind the secure perimeter of Area 51, work continues on concepts that may render these approaches obsolete. Recent satellite imagery shows significant expansion of facilities at Area 51, including new buildings with unusual features like extremely large power substations and sophisticated cooling systems, infrastructure consistent with high-energy physics experiments, or advanced propulsion testing. Increased activity has also been noted at the Tonopah Test Range, a related facility often used for the transition of technologies from pure research to practical application. There are also intriguing patterns in the scientific literature and patent filings. Occasionally, concepts appear that seem to have no clear developmental lineage, representing quantum leaps rather than incremental advances. Some of these may represent technologies that have been selectively declassified and released into the public domain, either because they've been superseded by even more advanced systems or because strategic advantages now favor disclosure over continued secrecy. Indeed, the recent acknowledgement by the U.S. government of the Advanced Aerospace Threat Identification Program, AATIP, and the release of Navy videos showing unexplained aerial phenomena may represent a shift in how these technologies are managed. Some analysts suggest that these disclosures might be preparing the public for the eventual revelation of advanced aerospace technologies developed within classified programs, technologies whose performance might otherwise be mistaken for non-human origin. The implications of the Space Technology Division's work extend far beyond military applications or even space exploration. The physics being explored touches on the fundamental nature of reality: space, time, energy, and matter. Breakthroughs in these areas could transform not just how we travel through space, but every aspect of human civilization, from energy, production to transportation, communication, and manufacturing. Consider the implications of practical gravity control, one of the division's long-term research goals. Such technology would revolutionize space launch, making access to orbit as routine as air travel. It would transform construction, medicine, and manufacturing. It might even allow for the creation of habitats with artificial gravity, solving one of the most significant challenges to long-term human presence in space. Similarly, the energy technologies being developed could address climate change and resource scarcity, providing abundant clean energy that would eliminate dependence on fossil fuels and transform geopolitics. Advanced materials could revolutionize everything from consumer electronics to infrastructure, while breakthroughs in quantum communication could render current encryption methods obsolete while enabling new forms of instantaneous global connection.